I would like to introduce you to our second speaker for the evening, Dr. Gautham Narayan. Gautham is an Alaska Fellow here at Space Telescope Science Institute. He works on using our space telescopes to follow up rare and interesting sources discovered using data science and machine learning techniques from big ground-based surveys. Dr. Narayan received his PhD from Harvard University. This evening, I challenge you to reach out, unleash the scientist within you, ask questions, and don't be afraid to dream big. Without further ado, please join me in welcoming Dr. Gautham Narayan.
Switch out. Give us just a second to get switched out over here.
One second. And also, parents, I know you're going to hate me. All right. Yeah, y'all did a great job. So down the table, please help me. Get it out of Mr. Harris' house, please.
Okay. Can you all hear me? Awesome. So I'm Gautham. Thank you for that introduction, Tanya. She got that, I think, off of my webpage, but I want to give you sort of more of a flavor of what I do. I study stars that blow up. That's my life, okay? I, like most kids, liked things that caught fire and had made giant sounds with explosions, and I simply made that a career. So what I'm going to talk to you about today is how stars get to that point, okay? You've seen stars in the night sky. Do they change? How do they change?
Over time.
They change over time. Excellent. And we've seen this happen. We've seen stars change over time. This is one particular star like that. It's SAO 244567, and the star, as you saw in that little video, it's shrunk, it's gotten red, bluer, and then it gets redder, and towards the end of its life in the far future, it'll end up like that weird little, not a supernova, but we will talk about supernova. I'll play that video again for you. So you'll actually see it end up in what's called a planetary nebula, and this particular star will form a white dwarf in the middle of that planetary nebula. So we've actually watched the star for years, and this will do this around, in another 500 years or so. It's a very slow process, but stars evolve. Stars change over time. They're changing all the time. It's just that most stars live for billions of years, and so you really never see them change individually necessarily. But if you look at lots and lots of them, you can see them change. So the first question I've got to ask you folks, and this is a hint, how do you study stars? In the back, with light. We look at light with mirrors.
Prisms.
With prisms. Anybody else?
Infrared light.
This man said infrared light. Wonderful. Pat yourself on the back. We'll talk about them. So yes, the common theme in all of these things is that we will study stars with light. I will get to you. Don't worry. We'll have lots of questions on this entire talk. I'm so glad you got all that excited. Here's a picture from the Hubble Space Telescope. Quick question. How many stars can you see? You can see billions? I can see like 6. Like 1, 2, 3. Just shout out numbers. Shout out numbers at me.
300 or so.
40, 300, 1. 90, 70, 60. All right. So somewhere in the less than 100, okay, in this image. Is that fair? Is that reasonable for all the answers I had shouted out at me? That's a rough count, right? Try it now. Way more, yeah? Way more. What changed between those two pictures?
stars in more detail.
We can see more stars in more detail, but why can we see these stars in more detail?
Because you could see more of the light.
We saw not more of the light, but different light. Gentleman over there who earlier said infrared light, he hit the nail on the head. What we were doing was looking at light that your eyes could see in the first picture. This is what your eyes would see. It's roughly the optical part of light, something what we call roughly blue to red. This is what you see when you move into the infrared and you can look through all of these pillars of gas and dust. These are called the pillars of creation. They're a very, very famous system up in the Eagle Nebula. And you can actually look at these things through some of the small telescopes, well, if it wasn't cloudy tonight. So what I'm trying to the point I'm trying to get at here is that where you look at the light matters. If you look in the visible, you get a very different picture of the universe than if you look in the infrared. And so what we do as astronomers is mostly study rainbows. We look at light all across the entire electromagnetic spectrum. And so when you split up the light from a star, this is something like what you get. It's something like what you see if you put light through a prism, right? What are the black lines? Anybody want to guess?
Absorption lines.
Absorption lines. Young sir, how old are you?
I learned this in class.
You learned this in class. Well, should you need a job, I'm sure the Science Institute would love to hire you. That is exactly right. These are the absorption lines of chemical elements here on Earth. These big ones are hydrogen. And then there are a whole bunches of other things. These are iron lines in here. There's a famous doublet from sodium. And so when you look at starlight, you're seeing a rainbow, but on that rainbow is the chemical fingerprint of all of the things in that star. And we only figured this out really in the 20th century. And it's kind of an amazing thing, because back in the day, we didn't have digital cameras, so people were recording these things on glass plates. And they were recorded mostly at Harvard College Observatory. Wilhelmina Fleming looked at all of these glass plates one by one, and she simply started to label them. She said, oh, this one's an A, because it's the first one I've seen. This one's a B, because it's similar to the A, but not quite the same. And she made up a scheme of that sort of labeling these spectra of these stars, these rainbows. And then a few years later, Annie Jump Cannon realized that what Wilhelmina had actually done was create a temperature sequence. Some stars were hot, some stars were cool. And so they had different kinds of spectra that way, different rainbows. And it wasn't until sort of the mid 1950 odd, when Cecilia Payne-Gaposchkin realized that what you were really looking at was temperature and chemical ionization. So these stars, it was only in the 1950s that we realized what they were made of. And it's really weird. They're made of hydrogen and helium. Stars are just giant gas balls. That's kind of strange, because hydrogen and helium, they may be really prevalent in the universe, but you don't really encounter lots of it here on Earth. Yes, sir? You had?
The helium and the nuclear reaction and forms.
You will also have a job at Space Telescope very shortly, should you apply. But so what we want to do is actually get to this point. And so I need to drop some jargon on you, and I try to explain the jargon when I use it. You've all seen sort of things like plots. This is a x-axis and a y-axis, and these are two numbers of x versus y, right? It's not a complicated concept. If I say something is increasing, it just means that y is getting bigger as x is getting bigger. A spectrum of a star, that rainbow that I showed you, only corresponds to this tiny part. This is what your eyes can see. This is what your eyes have evolved to see, because this is what the atmosphere lets through. But light comes through all over here. So there's gamma rays and X-rays, really high energy radiation, and then the ultraviolet, which is why you use SPF 50 or whatever, and then the infrared radiation that we mentioned, but there's stuff even beyond that, radio waves and microwaves. And so we record the signal from starlight, or all kinds of light, at all of these different, over this entire range. And then we can also record how bright the star is across all of that different range. And if you just look at this picture, you can see that some stars are brighter than other stars. Some stars are redder than other stars, right? That's just visible and easy to see in this picture, but we need some way of communicating that information to people. And so we use a spectrum, and a spectrum is like that rainbow from left to right, but just in the form of a plot. And where you have dips in the light, you have dips in the plot, right? So this is a star that has hydrogen elements here, 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 there. And so this is a plot. It's nothing more complicated than that, right? And you'll be seeing a few of these, so I want to show you them. But this is how different stars look. O stars have rainbows that have essentially no black lines. And then as you go down the list, you start to see more and more of these absorption features come in, right? So there are different kinds of stars. These stars are very blue. These stars are very red. There's almost no blue light here because they all are getting absorbed by all of these features, right? And we can see that if you look at a plot of all of these things. These stars have more light in the blue than the red. And when you go around here, they are more red than blue. So this is really what we're seeing. And what the chemical elements that you see in these stars, that's the periodic table that you might have seen in a classroom. Okay? And I'm going to tell you something that is one of the takeaway points from this talk. Every one of the chemical elements that is in a star spectrum, every one of the chemical elements that's in you, they're all from a star. And then somebody mentioned nuclear fusion. You did. And that is the power source for these stars. So what nuclear fusion is taking the hydrogen that stars are made up of, that Cecilia Payne-Gaposchkin realized was what was in the star spectrum, and converting it to helium, and that process releases energy. Stars shine. The energy has to come from somewhere. This is how it comes out. But then you might have a question. If stars shine and release energy, why don't they just like puff up and dissipate? And we can see what happens to flames when we do that, because Russian astronauts were crazy enough to light flames in the Mir space station, and this is what happens to flames in space. They puff up, and then they expand and slowly disappear. So why do stars stay the same in the sky?
The nuclear fusion is like making it go out and trying to make it explode. Gravity is pushing it in and trying to crush it. And together they make the star. So that is what you
I was going to have to use this as a prop and toss an apple to see if somebody would catch it, but I think you've earned it. So that's the answer. The answer is that gravity is holding stars together. They are burning fuel. They want to expand really fast, but then something is holding them back, and that's gravity. And this is kind of a strange thing, right? If you think about gravity, it's a really, really weak force. The entire planet is pulling down on this apple, and I'm still able to toss it. The entire planet is pulling down on me, and I can jump. It's a really pathetic force. But when you're in space, that's really all there is. And what's happening in space is that clouds of gas and dust are being pulled together under gravity and getting hotter and denser. And in the center of those clouds and gas and dust, where it's the most hot and dense, that's where stars are born. Those pillars of creation, where all those, which you couldn't see through, all that dust, that's a factory for making stars. Gravity is causing stars to form inside the pillars. And we've seen this. These are actual images from Hubble. So these are disks called Herbig-Haro objects, and they're disks of gas and dust. And you can see stuff falling into them, and it's these things that are going to be producing stars, like the pillars that you saw. This one's just on its side. And so this is the basic picture that we have. Stars are basically always fighting. And it's a fight between nuclear fusion on one hand and gravity on the other hand. A star does start from a nebula. This is, in fact, a nebula. This is, in fact, the name for a nebula. I'm trying not to introduce jargon that I don't need to. But yes, this is a nebula that will form a star. And so, like I said, stars are a constant battle between fusion and gravity. And the star is going to lose. So gravity is trying to cause the star to collapse. The heavier the star, the higher is gravity. The fusion is releasing energy, preventing the star from collapsing. The more fuel stars can have more fuel because they're heavier. So the fates of stars are basically determined by how massive they are. Does that make sense? Okay. And we have in a galaxy something like tens of billions of stars, hundreds of billions of stars in something like our galaxy, which is fairly big. So this is a massive thing, but the distances between stars are also massive. This is why we aren't all being vaporized by nuclear fusion. So even if you were able to travel at the speed of light, the nearest star to us is 3 light years away. That's Proxima Centauri. And other stars are even farther and farther apart. So galaxies might have 100 billion stars, each of which is about as massive as our sun, each of which has lots and lots of energy and is producing energy through nuclear fusion, but they're really far away. Galaxies are not very dense things. So the fates of stars, you can study them even though for a single star you can't really see stuff change very much over a human lifetime. You can see them because there are hundreds of billions of stars in the galaxy. And like we said, stars start off at some kind of molecular cloud, which starts to contract, and it gets hotter and brighter as it contracts, and also smaller. And then it starts fusing hydrogen to helium. And when it does that, we say it's on this thing called the main sequence. If a star is not massive enough, it won't form fusion. What do we call these things? What? At the back, sir. Some of these things are white dwarfs, but white dwarfs are actually stars. They're the end products of stars. We call them something else. Brown dwarfs are a good name for some of these kinds of things. Other ideas of what sort of things these are? You in the back?
Red dwarfs.
Everybody's stuck on dwarfs. What do you don't like dwarfs for?
So they're smaller.
Nebula maybe?
A nebula? No, it's roundish.
Ulcers?
Ulcers, we'll get there.
Asteroids?
What's Earth?
A planet?
Yeah. It also formed very much the same way. Jupiter, for example, you can think of it as a planet. It's also a failed star. It's a star that didn't actually start fusion. It is a gas giant. And some stars, when they get too massive from this process, they become unstable. We'll get there in time too. So you can actually see what happens to a star like our sun. They start off in a nebula, and then for most of their lifetime, nothing interesting happens. So our sun will be about 8.2 billion years. You won't really see much of a difference. And then in that last 11 billion years, it'll puff up and become really, really big, a red giant star. So this is the sort of lifetime on the main sequence. This is what stars do. Virtually nothing interesting for the vast majority of it. And then right near the end, puffing up massively. Say one more time.
So what would be the result of the sun puffing up?
What would be the result of the sun puffing up? In about 5 billion years, when the sun does that, all of the inner planets, so up to about Mars, will get completely cooked. So your home real estate values are going to plummet. But it's 5 billion years, so you don't have to worry about it. Jupiter will get cooked and vaporized in the process, and most of the things that you know and love will have changed. But we don't have to worry about it because 5 billion years, we've got time. So stars only have so much fuel, right? They are constantly in this battle with gravity, and they are losing this battle. They are burning fuel to prevent themselves from collapsing. And as they're burning fuel, as they're burning hydrogen to helium, helium to carbon and oxygen and nitrogen, nitrogen to sodium, sodium and other elements to even higher elements along the periodic table, their composition is changing. They're producing new things, their properties are changing. And so we can see what happens along the main sequence. Our sun is around here, but there are stars that are less massive than our sun. They're all red. And there are stars that are much more massive than our sun. They're all blue. So I'm now connecting how massive a star is to all of those spectra, those rainbows I was trying to show you earlier. Right? These stars up here, those are the O's and the B stars that you never saw, that had virtually no absorption lines. Stars like our sun are normal. White dwarfs and things are really tiny, and they're down here, and we'll talk to them about them in a second. And so this is really how stars live and die. And as they run off of fuel, they'll move off of the main sequence. And there are a couple of ways to move off the main sequence. There's this area over here, the supergiants, red giants, blue giants. There are these white dwarf stars down here. And the star is beginning to die when it does that. It's running out of fuel. And we've seen this. So this is a star called V838 Mon. It's getting near the end of its own life. And when stars get near the end of their life, they sort of burp and let off a whole bunch of light. They get a little bit brighter. And when that light runs into the material that the star has shed over the last few million years, something cool happens. So this is actual images. These are images from Hubble. And so what you're seeing is what the star had let go of in the years before V838 Mon let off that burst of light. So you're seeing the material of the star being shed as it's slowly dying. It's getting bigger, it's getting puffier, it's losing its outer layers. Yes, sir?
Don't white dwarfs collapse on themselves and become black holes?
We will get there. Yes, they do. So we will get to white dwarfs and black holes in a bit. So a star like our sun, which is around here on the main sequence, will slowly start to increase its temperature, get brighter, and increase its size. This is its size and sort of relative to the sun. So this is a logarithmic scale. So this our sun will puff up to about 10 times its original size, and then even bigger, then drop down, and then slowly become what's called a planetary nebula, and then end up as a white dwarf. That's the fate of our sun. And we've seen these kinds of planetary nebulae before. These are, again, images from Hubble. These are some of the most colorful and beautiful things that you can see with a moderate telescope on a clear night from a dark sky. They're absolutely beautiful. They have emission that essentially is telling you all about their chemical composition. And so, should you go out with a telescope sometime, try to find some of these. They're really fun to watch. So somebody mentioned white dwarfs, and somebody mentioned black holes and neutron stars, and all of these ways are ways that stars die. Stars around the mass of our sun, they'll eventually end up as white dwarfs. Stars about 4 to 8 times the mass of our sun, they end up as neutron stars, and much more than that, they end up being black holes. But there's just arrows here, and this process, the arrows of going from here to here, that's what I study, is how these stars actually die. So for a white dwarf, for the most part, if it ends up like something like our sun is a white dwarf, it just sits there, radiates heat, gets cooler, slowly, for basically the entire history of the universe. It's not going to do anything exciting, except if there happens to be another star around it. And then it gets mass from that other star. And then something in really real occasions can happen. That sort of thing. I'll play that again. So that's a supernova. That's a star that's exploding. That's what I study. This particular kind of supernova is called a type 1a supernova. And this particular one is I believe, 1998 BU. And it's in a galaxy that you can go look at with a telescope. But what I want you to appreciate is here is a galaxy, which, like I said, has about 100 billion stars. Here is one single supernova that is shining brighter than all of those 100 billion stars. That's a lot of energy. In fact, that's about as much energy that the sun will put out in its entire lifetime, except in the space of a month. Entire 10 billion year lifetime, same amount of energy in a single month. That's crazy. So supernovae are really powerful explosions. They get bright and then they slowly fade away. If you look at them in the optical and the infrared, they have slightly different shapes. The person who figured this out, Subramanian Chandrasekhar, is an Indian physicist, one of my sort of heroes to follow why I'm doing the sort of things I'm doing. There are other ways to blow up stars, some stars that are more massive. And yes, sir.
Black holes at the middle of a galaxy and they're as strong.
They are very strong, but they aren't very bright because they're black. We'll get to, in fact, black holes in a bit. But the kind of stars that this is are how you actually produce black holes in the first place. So massive stars that are sometimes more than 8 times the mass of our sun, they die very different deaths. And the best video for them is actually from a movie called Superman.
We'll travel far.
So hopefully we have audio somewhere in this room.
But we will never.
But if not, what you're looking at is the planet
even in
Krypton.
the face of our death.
The planet Krypton
Will make my strength
is around a dying star. This is Superman's capsule, so
You'll
it's
see
zooming out
my
towards
life
Earth.
through your
And as we're
eyes.
zooming out, we'll see the sun
As your
of
life will be seen
Krypton,
through mine.
which is some massive red giant
The
star,
sun becomes the father, and the father the
much like this.
The
And this
sun.
star has used up most of the fuel in its core, and something horrible is going to happen to it. No more fuel, nothing to prevent gravity from causing you to collapse, so it collapses, and it literally collapses in seconds. Little explosion. Krypton's gone. So this is a different kind of supernova. This is a core collapse supernova, and often what's left behind when these things happen are neutron stars and black holes. The core becomes so dense as all of that material from outside rushes in that it forms a neutron star or black hole. And this was made by Hollywood for a Hollywood movie, but it's accurate because it was also, they consulted astrophysicists. Yes, ma'am.
What's the span of, so you have a galaxy, you have a star that collapses in on itself and creates a black hole. What's the span of how much will go into the black hole? Will it be the entire galaxy? Would it be
No.
So what's the span of how
The mass hasn't changed, right? The star is still the same mass. So in fact, the gravity is not going to change. What's going to change, the strength of gravity isn't going to change when you create a black hole. It's still all of the mass of stars. What's changing is the density, how small things are. So in fact, for things that are far away from that star that exploded, nothing will be different. They don't suddenly get sucked in. It's not like a vacuum cleaner pulling it in. They just move on as if nothing else happened, because nothing did as far as they're concerned. So the answer is it makes essentially absolutely zero difference. Until you're close to a black hole, you won't even be able to tell the difference between normal space and a black hole. Yes, sir.
Doesn't the black hole's gravity increase when the star becomes a black hole?
No. It's still the same mass of the star. We still have to conserve that mass. It's not going to change.
Right.
So was that bigger than the sun, our sun, and what would it be would it become a regular supernova, or is it like going to be like one of the black holes?
So something I forgot, our sun will just form a white dwarf and sort of cool for the rest of the lifetime of the universe. It has to be quite a bit bigger than our sun to create something like these, like 8 to 10 times as massive. So we can see what happens when a star explodes and what's left behind from these supernova explosions. Essentially, you've taken all of the fuel in the star very quickly, tried to cook it from hydrogen and helium all the way up the periodic table. And so what you see when you point Hubble and all of our space telescopes at it is every kind of atom that's produced on the periodic table. All the calcium in your bones is from one of these dying stars. When we say you are made of star stuff, that's where you came from. And these things are still exploding. This is a remnant of a supernova that happened in sort of 1572. It's called Tycho's supernova. And it is still expanding to this day. So if you watch these frames and watch the outer layers, you'll actually see things move just a little bit. So it's still got energy from that original supernova explosion back in 1572, and this thing is still spreading to this day. We can see this also in a galaxy near ours. Adults in the room, do any of you remember a supernova named 1987A? It was the first supernova in 1987. You would have only seen it if you were in the southern hemisphere, but you probably heard about it in the news because it was a big deal. That supernova is still being watched to this day with Hubble, and it's producing, it's releasing energy, and you can see this ring of material around that supernova's position light up over time. So these things are really still engines. These are corpses of stars. They've died, but they're really actually producing life. And all of the things that you see around you are from these corpses of stars. If there's actually one point I want you to take away from this talk, that's it. So people were really excited about things like neutron stars and other things like black holes. And so I felt we should talk a little bit about that. A neutron star is something roughly the size of Baltimore, but with about as much mass as the entire sun. So it's a really dense, really compact source. You can mostly see them in sort of X-ray and high energy areas, so stuff like gamma rays. And so we look at them with a different space telescope, not Hubble, but one that's called Chandra, named for the gentleman whose picture I showed you earlier, Subramanian Chandrasekhar, who figured out how the supernovae work. Sometimes these neutron stars spin, and I'm hoping we again have audio, and maybe we can even turn up the volume some, because here's how some of these spinning neutron stars or pulsars sound. So this is a typical normal boring pulsar, and it's rotating with a period of around 1.4 times a second. And so you can actually turn the radio waves into audio and hear what this thing would sound. But of course, pulses come in a range of sound, so I'm just going to... This thing is rotating 11 times a second. This is a Vela pulsar. Of course, things can go more extreme. And then there are pulsars like this thing, which is 174 times a second. Sounds like a bee or something. Pulsars can get even more extreme if they're spun up by other stars like this one is. And so we have things called millisecond pulsars. I want you to remember this is something the mass of the sun spinning thousands of times a second. These are some of the most extreme objects in our universe. We've also seen what happens when neutron stars now come near each other. So like white dwarfs, sometimes if you just have a neutron star, it just sits there by itself. But every now and then you have two neutron star systems around each other. And for the first time last year, we saw what happens when one of these blow up. And we call these things kilonovae. And they're really cool because the explosions are so intense that they actually distort the fabric of space-time itself. We get what's called gravity. These kilonovae split into each other. All of them. I'm glad you like it. That was huge. What would you like to say?
Black hole basically rips in space-time. Same open space-time.
You can think of them that way, yeah. So the kilonova, like the supernovae, produces lots and lots of energy, but it does it, instead of a month, it does that same amount of energy in just a few days. So even more extreme than a supernova. And this thing had to be followed up by observatories around the world to be able to map out how it was done. We've only found one of these so far. So we're really excited to find more in the near future and follow them up with things like Hubble. Now, throughout this talk, of course, there's been a huge amount of excitement about black holes, so it would be remiss of me to not talk about them. Black holes, like the gentleman just said, they are sinkholes in space-time. You can't really see what they look like, but they distort the entire fabric of space-time. And so you can see here, for example, as the black hole, in this case, is passing behind some background galaxy, it actually changes that shape of the galaxy. we can actually zoom in very closely to the black hole in the center of our galaxy. This is from the European Space Observatory. And so we're zooming in here, much like CSI, right into the center. It's like enhance, enhance, enhance. And you can see what stars are doing near the center of our galaxy. And you can see some of these things moving around. And so you can sort of model them. And if you model the stars near our center of our galaxy, you find them that they are following ellipses, much like the planets in our own solar system. And those ellipses are around something that we can't see. One particular star, S2, actually forms a nice complete orbit in about 16 years. And so we can use that to tell you exactly where the black hole in our galaxy is and how heavy it is. But we can't see anything there. Yes, sir?
So, do you think that it's a portal to like a different planet? No.
That is a subject for science fiction. And I could tell you all about that in another talk. If you come to Baltimore Comic Con at any point of time, I'll be doing a panel there, hopefully, on black holes and space travel and wormholes and things of that nature. But we don't know is the answer. You wouldn't want to find out. In most cases, as you would try to find out, you would probably get cooked. So like I said, black holes and gravity, they distort space itself. They distort space itself, of course, not even just in our galaxy, but also around space, around other galaxies. So this is a cluster of galaxies. All of these red dots here are massive galaxies. And then there are galaxies in the background to this one. And every now and then, you see a star go supernova in one of these galaxies. So this particular galaxy had a supernova that went, or a star that went supernova. But because space is distorted by this cluster, we got to see 4 images of the supernova being produced. So we call this supernova Ref's doll. This was imaged by Hubble. And it's gravity literally changing the shape of space, called gravitational lensing. We've actually seen 5 images of this thing at different times. And so you can see here, because each of these galaxies has 100 billion stars, it's really warping this one galaxy into several different images and actually changing the very shape of space. Black holes are really monstrously heavy things. And so they're accelerating jets of matter. This is, again, a galaxy. And you can see jets of matter shooting out of it, several times the size of the actual galaxy itself, at near the speed of light. And we call some of these things gamma ray bursts when they happen as well. So the sort of summary for the lifetime of how stars live and die is that stars begin their lives as star-forming nebulae. Some of them, like our sun, slowly collapse out of this star-forming nebulae and become regular stars. Those live and become red giants. Some of those end up as planetary nebulae. Stars like our sun will end up as white dwarfs. The planetary nebulae themselves create birth to the next generation of stars. More massive stars start their life off, become red supergiants. They all end up in supernovae. These are the things I study. And then those produce the more cool neutron stars and black holes that you were all excited about. And what's left from the supernovae, again, forms the next generation of stars. And this recycling process is important because this is where you come from. These are the planetary systems around the next generation of stars will now have all of the elements that were produced in that supernova explosion. So the universe is recycling, and you should too. That's about all I had for you today.
Let's give another round of applause for both of our speakers. We'll take about 5 minutes of questions, so we'll take about 5, but either one of our speakers this evening. So if you have any questions, feel free to ask. And if we run out of time, after we go to the next part of our program, you're welcome to stay behind to speak to our speakers for a few minutes. So does anybody have any questions?
What college did you go to and what did you study?
So as an undergrad, I was in a small liberal arts school called Illinois Wesleyan University in Bloomington, Illinois. It's a little bit south of Chicago. It's like 2,000 students. You knew everybody. I worked at the coffee shop. Everybody loved me because I gave them coffee. And it had a very competitive little physics program, which is why I went there. The other reason was tuition was free, and I was from India, and I couldn't afford it otherwise. After that, I went to Harvard University in Cambridge, Massachusetts, which is a much bigger school. I did my PhD over there, moved to Tucson, where I worked at the National Observatory there first, and then moved here last year.
So your undergrad was physics and your master's was?
Also physics. My PhD and master's were physics. So I have a dirty secret. I've never actually taken an astronomy class. I've taught astronomy classes, though.
Okay, we have a question over there.
What's the process of a supergiant going supernova?
That's a great question. So, what is the process of a supergiant going supernova is called core collapse. So, as stars burn up their fuel, the hydrogen becomes helium, the helium becomes carbon, nitrogen, oxygen, and this goes all the way up to iron. And then something happens because you can't fuse iron and get energy out. So basically, iron is the peak element that you can produce in the periodic table. And after that, any energy, any heavier elements that you can produce, they take in energy and give out less energy in that reaction. So there's decreasing and decreasing amounts of all of those heavy elements. So what happens in a star that's going supergiant star is its core first starts off with the hydrogen, goes all the way to helium, and then gets to iron. And then once it's gotten to iron, it can't fuse iron and produce any energy. So the core begins to collapse. The layers around the iron part of the core are slightly lighter elements all the way up to hydrogen. And then, so it's like an onion structure. It's like iron in the center, slightly less heavy elements outside, all the way up to hydrogen. But once the iron part stops fusing, there's no more energy preventing all of this thing that's 8 times the mass of the sun from collapsing. And so it just goes. Other questions?
This will be the last one, and then we'll start the next part.
Right. What elements make the most like a deadly star?
A deadly star?
Like those that were like as soon as we came up to it, it would get you into the rocket.
So what environments, I guess, make a deadly situation for a rocket ship? That's a really good question. Stars by themselves aren't deadly. It's space itself that's deadly. So in our universe, there's just so many stars. Some of these things are producing high energy radiative particles, cosmic rays we call them, but they're really just electrons and neutrons and particles that have really, really high energy near the speed of light. And they'll hit the fabric of your rocket ship all the time. And so you're being constantly bathed by radiation. It's like you're sitting inside an X-ray room, constantly getting hit by X-rays. And that's actually what will do the damage. It's not the star itself, because we know where those are, and we'll mostly, presumably avoid the sun in our rockets. It's these high energy particles from gamma ray bursts and things of that nature that are slowly degrading our rockets and our satellites in orbit.
Thank you again.
All right.